Today we're going to be looking at inverse functions, section 5.7 in our textbook. We're going to focus on the finding of inverses today. We'll also talk a little bit about graphing inverse functions, but we'll do more of that tomorrow. You're going to get a little bit of that today. Actually, regardless. So here's what inverse functions are. Inverses are functions that undo each other. Here I've got two functions, and these are inverses of each other. You wouldn't know that, except I'm telling you they are. Okay, but it kind of makes sense. They undo each other, so function f here takes whatever x is and adds 1, and function g takes whatever x is and subtracts 1. So they do the opposite of each other. But here's the important thing that inverses do. Let's say I wanted to find, and I'm picking a number at random here, the f of 4, and that means substitute a 4 into the function. So it'd be 4 plus 1, or 5. Well, the inverse does something really neat. It takes the 5 that was output by function f, and when I put that 5 in, it returns the 4. And remember, 4 is what I started with. So the original function, it took a 4 and maps it to a 5. The inverse function g, it takes the 5 and returns it or maps it back to a 4. And that's all an inverse does, is it undoes perfectly what the other function did. You have these things all over your calculators. On your calculators, you have a physical button that says x squared. And then if you press the second on your calculator, there's a function button. Anyway, above the square button is its actual inverse, which is the square root. And so most of your buttons, or quite a few of your buttons, are set up so that the button has one function on it. And when you hit the second button, it used to be the inverse button, it pulls up the function above it, and that function is the inverse. And it turns out x squared and square rooting are inverse functions. So keep in mind, these things are important. They're actually used on your calculator, and that's how your calculator is organized. Now, these two functions were relatively simple. One added the number 1, and the other one subtracted it. So let's look at a more complicated pair of inverse functions. And here they are. Here's f of x. And here is g of x. These are inverses, and we can actually see in their data tables here. I've just plugged in some x's and out came some y's. But you'll notice then I took these y answers and I've put them back in for the x's in function g, and out comes the original numbers. So you can see, like, when I plug 0 into f, out comes 3. When I plug 3 into g, out comes 0. So it undid what the other function did. But these are much more complicated in comparison to that add 1, subtract 1 function. In this case, this function doubles the x value, then adds 3. The inverse function subtracts the 3 and then undoes the multiplication by dividing by 2. So it's just, instead of an add 3, it's a subtract 3. Instead of multiply by 2, it's a divide by 2. So it undoes what the other function did. Now, when you do have inverse functions, I want to clarify what notation looks like. If I were to just give you these two functions, you wouldn't know they were inverses unless you investigated them. So we have some notation that helps us know without somebody telling us that they are inverses. And so since g of x is the inverse of function f, the notation looks like this. We actually use the name of the function we have the inverse of, f, and then we put a little negative 1 up here. It looks like an exponent. It's not. That just means the inverse of function f is what? It's that expression right there, x minus 3 over 2. Because there is such a strong relationship between a function and its inverse, graphically they actually have a distinguishing characteristic. So here I've graphed these two functions. Here's the first function, and this is the inverse over here. I might as well start using that inverse notation. Let's do it in red so we match up here a little bit. So I should probably write it this way. to indicate it's the inverse of that blue function, or the function f. But what we'd like to point out is because what happens is the function takes x's and maps them to y's, and the inverse takes the y's and maps them back to x's. When we graph them, we get this reflection across the line y equals x. And so the blue line, the original, and the inverse are mirror images across that line. Okay, if I were to fold this graph right on that dotted line, the blue and the red lines would lay right on top of each other. And all inverse functions have this characteristic where they are reflections about that line. Such visually, we can actually see if two functions are inverses. We'll talk about graphs a little bit later in more detail. Now, let's go about the steps for finding the inverse of a function. That was the first thing we wanted to do. So let's say we have this function right here, f of x equals 2x plus 3, and I'm supposed to find the inverse. Well, I've got 4 steps here to do it. Step 1, change the notation. Okay, so for us, our step 1, if I'm doing this blue function up here, let's get this nice and clean before we start. So let me write down the function that I'm starting with. And I go, all right, find the inverse of f of x equals 2x plus 3. And I'm going to go step 1, change it to y equals. And I don't know why I put a 1 there. Change it to y equals 2x plus 3. So that's step 1. Step 2, you just got to know, if you think about the inverse function takes the y values, turns them into x, uses them as x values. And so it actually flip-flops your x's and y's. When you're finding the inverse, you actually do that with the variables. You take where the y is and put an x, and where the x is, you put a y. So you flip-flop them, exchange those. You're going to do that every single time. Now, step 3 is where the real math happens. In step 3, we have to solve for y. So here's our y value. Okay, we want to leave that alone, and we're trying to get stuff away from it. So we'll undo additions first. We'll subtract 3. That gives us x minus 3 equals 2y. And we almost have y alone. We'll divide by 2. And I'm going to flip the whole thing around. Y is alone now because 2 over 2 is 1, and it equals x minus 3 over 2. I've solved it for y, and in step 4 now, I use that inverse function notation, and I write down the function I found. So there is the inverse of the function, and that's it. Let's take a look at another one. We've got f of x equals negative x squared. And it also says state the domain. Well, I'm going to state the domain. I'm actually going to restrict the domain. This should have been part of the problem. I'm just going to say an x is greater than or equal to 0. And there's a reason we're going to do that. So there's my function and its domain, and we're going to find the inverse and state the domain of the inverse function. So step 1, we change it to y. Step 2, we exchange x and y. Notice I've kept the negative sign where it's at. I've kept the squared where it's at. I've just changed the x to a y. Step 3 now, I'm going to solve for y. So I'm going to divide away the negative 1 first, giving me negative x equals y squared. And then I'm going to square root both sides, and I'll get y equals plus or minus the square root of negative x. Now, we do have that plus or minus, so it's going to be a little bit complicated to try and figure out, okay, do I want the plus root negative x or the minus root negative x? And this is where this concept of graphing is going to help us. So the first thing I'm going to do is, and I could pull up Desmos for this if I wanted to, but I'm going to graph y equals negative x squared. Now this is a parabola because it's x squared, but this parabola is almost like the parent function, except that negative sign, remember, makes it go downward. So that parabola looks something like this. But x is being restricted. At the very beginning, they were told, or I told you, restrict it to x is just greater than 0. So that's this side of it where x is positive. So the original function we actually are graphing does not include the left-hand side. It looks like that. Now here is the line, y equals x.
Now, since the original function was just the bottom half, remember I showed you how there is symmetry about this line y equals x. The inverse of this function is going to have to kind of go like this to mirror. In fact, we can kind of sketch it in here. The inverse, let's do it in green, but you have to look something like that. So that when you fold it over on that dotted line, they would lay on top of each other. But the point is, you can see here that the x values that have to be put in here are going to be negatives, and the only y values that come out are positive. And since only y values come out, the only y values that get graphed are the positive ones, so we do not want plus or minus here. We just want the positive. So our final answer for the inverse, changing it to the inverse notation, would be f inverse of x is equal to the square root of negative x. Next example, and really we don't need to state the domain on these. I'm not sure why that was in their directions, so we're going to get rid of that. Let's just find the inverse of this function. It does have an inverse. We could graph it and we'd see it. So let's go ahead and walk through those steps again. Step 1, change it to y. Step 2, where there's a y, put the x, and where there's the x, put the y. Highlighting that change in red there for you. And then step 3, let's solve this. Let's get that y alone, so we undo any addition or subtractions. There's the equal sign, dividing our equation into a left and a right side. That gives us x minus 4 equals negative y cubed, and the 4's are gone. Next, let's undo any multiplication or division. So I'm going to divide by negative 1 on both sides. On the left side, that gives me a negative x plus 4 equals y cubed. And then we've talked about how to solve cubic equations in this chapter where we cube root both sides. And when I do this, I get y equals the cube root of, and instead of negative x plus 4, I'm going to put 4 minus x. It's the same thing. And then lastly, we'll write it in function notation for our final answer. And there we go. That is the inverse function. And our last example, again, forget about the domain part. Y equals square root of x plus 2. We're going to square both. Oops, got to flip-flop first. Almost forgot. I was thinking about something else. My x becomes a y. Now we're going to square both sides to solve for y. So I square the left and square the right. This is a radical equation at this point. When I square x, I get x squared. On the right-hand side, the radical is now eliminated, and I subtract 2. I'm going to rotate the entire equation. Y equals, I'll have an x squared minus 2, and then we write it in the correct notation. and that would be the inverse function. And you can test these now. The way you would test them is find the f of some number. So you want to choose carefully. Here's function f. I'm going to use x equals 2. And I chose 2 because when I substitute 2 in for that x right here, I end up with the square root of 4. And the square root of 4 is just 2. This isn't going to be very eventful. Let's try it. Because then what I would do is I would take the f inverse of this 2, and so I'm pulling up the f inverse function, which is square the x, plug it in a 2, and then subtract 2. Well, that's 4. Oops. There we go. That's 4 minus 2, which is 2. So it returned the 2 that I started with. Let's try a different number so you can see it illustrated a little bit better. Let's do x is 7. And I'm choosing 7 because when I substitute a 7 in there, I know I get the square root of 9. So if I want the f of 7, it'd be the square root of 7 plus 2, square root of 9, or 3. And now if I take the f inverse of 3, it will be 3 squared minus 2, 9 minus 2. It would give me 7. So the point being, when you substitute a 7 into the function, out comes a 3. If you take that 3, put it into the inverse, it converts it back to a 7. It undid what f of x accomplished. That's it. Takes you to your assignment. Just 5 questions. Just find the inverse of the function.